now we can start recording. So what I was going to say that I stopped myself from, oh, you can't. I guess I have to plug this in too. My goodness. Too many plugs. One of these is what I'm looking for. There we go. Okay, there, for real this time. I will warn you, and I don't know what happened. I'm going to hope that it was just COVID related, and we just blame a lot of things on COVID. But back when we were doing student lectures for this course, they were great. Students had a blast, the topics were fun, the presentations were thorough, high quality, it was fantastic. And then like 2 years ago, they went to shit. The presentations were pathetic, absolute garbage, waste of everybody's time. I was getting angry. The students could tell I was getting pissed. Like, I was angry. And the exact same thing happened last year too. I don't know what the hell was going on, but the presentations for years before were phenomenal. They were great, students had fun, and then they went to absolute shit. Everyone's saying, oh, you know, we're out of the thick, you know, we're past all that nonsense. Yeah, it better be good. Because like the last 2 years, the average on the lectures were like 1 and 2. Like one person got like 8, no, like it was a group. No, that wasn't a group. That would have been, right, that was for the other. So it would have been 2 people did well. But even the good ones were shit. So don't be garbage. My expectations are back to where they should be. I don't know what happened, but if you are going to tell me that you are just intrinsically dumber than students 2 years ago, I don't buy it. You are not. You are at least as good. So I have expectations that they're not going to be garbage again, okay? So, you know, do a good job. Put in the effort. I want to be impressed. Yeah. Cool. Any questions about that? All right. Trying to think, is there anything else? We haven't figured that out yet. I'm waiting to finish all this other nonsense that I got to get off my plate before I can start thinking about that. You still know when-ish they're going to be done. They're going to be done like mid-November, so claiming that there's no deadline for a reason to not start that's a non-starter with me. You know they're going to happen, so yeah. Some people requested dates, I think, already, but I'll send out a follow-up email. The other issue is I've been dreading going through it because when I sent in an email, instead of replying to the email, everyone sent me random emails, and now I can keep track of who and when and what came from where and what they're even talking about, so it was quite difficult. Anyways, genetic programming. All right. Make sure recording is going good. Okay. All right. So, genetic programming, it's using a genetic algorithm. It really is just a genetic algorithm with a specific goal in mind. And that goal is to evolve programs, functions, whatever you really want to call them, same thing. The genotype is typically a tree structure representing the program or function. We already saw this, but we saw it really more in terms of like symbolic regression, which is when we had like mathematical functions, but it just is a program. And the genetic operators we're using work for that representation. And at the end of the day, it really is just a GA that searches the space of problems and functions. And typically, too, the goal, like when you're looking, in general, like a GA is more like a strategy for optimization, okay? Typically. Right? Maybe I shouldn't even say typically, but you know, it's commonly used like that. You use it for optimization. I want to find a good solution to this problem. Genetic programming is a little bit more like machine learning-y. I mean, when you start drawing lines between optimization and machine learning and this and that and AI, it's all the same stuff at the end of the day. But genetic programming is a little bit more machine learning-y. But of course, like I was saying, all of the lines between these things are all really fuzzy because, I mean, at the end of the day, we're just optimizing the program we're optimizing the function we get for like classification, for example. So the machine learning really is an optimization problem too. You're just optimizing. It's like, what are you optimizing? Anyways, was that clear? Hopefully. If not, I'll try to make it more clear as we go. So like think of TSP, right? TSP with, you're using a GA, you're looking for the best Hamiltonian cycle. Let's say you're doing like breast cancer identification based off of some observations. So here's some data, right, with some particular ID is just an ID. But we have some interesting like observations. Thickness of some, observations of patient tested for breast cancer. Of some like tumor, I don't know if it's technically called a tumor, but a tumor, the size, number, classification, shape, bare nuclei, mitosis, I don't know really, and then some classification, benign or malignant, okay? So this is some tabular data. If you're, raise your hand if you've done machine learning before. One person, really? Two people, okay. Well, this is your typical tabular data you're seeing for machine learning. You have observations, and you have measurements, okay? Your rows and columns. We typically present these things as rows of observations and columns of data for that respective observation, right? So the goal is, based on my observations, can I classify, like can I know, without going in and explicitly testing is this benign or malignant, can I, based on easier to obtain measurements, know if something's benign or malignant, okay? Benign is, it's not interesting. Malignant is, we got a problem, okay? So I want to know this. So a classic example of a situation like this, let's take a step back from the breast cancer classification. An example of something, like, this is a common problem where, like, I can use another example. At one time I was studying traumatic brain injury, all right? And we had, if someone gets hit in the head really hard and they have traumatic brain injury, we really want to know, like, do they need, like, neurosurgery, okay? And I can measure intracranial pressure of somebody. I can do that, but it requires neurosurgery, okay? I have to put this giant catheter into someone's brain. I have to drill into their skull and put something into their brain to measure their intracranial pressure, which is going to be very important for me to measure if someone has had a really bad, traumatic brain injury, okay? We don't want to give someone neurosurgery. So is it possible, like, that's expensive, it's risky, you have like a high mortality rate, there's a lot of reasons why we don't want to drill into someone's brain. It should be pretty goddamn obvious, right? So is there a way for me to get a proxy? Can I have a damn good guess of what a patient's intracranial pressure is without measuring it directly? Like if I know things like their blood pressure and their respiration rate, their O2 saturation, their heart rate, and a variety of other metrics that are easy to obtain. Things that I could just put a sensor, I don't even need to like put anything into them. I could just put sensors on them and I can have good measurements of these things. Could I know their intracranial pressure without having to drill for it? Because if I could, that'd be a pretty big deal, right? One, I don't need to perform neurosurgery if I don't need to. Because think about it, like if they want to save someone's life, they want to save someone's life, but they're really worried about the pressure inside their skull, and then they drill into it and they find out, no, everything's fine. Great, I just drilled into someone's brain and I didn't need to. It's not very good. So obviously that would be a good thing. So back to this particular problem, and the reason I use that example is because I knew it a little bit more. But going back to the breast cancer problem, which is a common, this is based on data from like a couple decades ago, I think. This is a common repository. Those of you that have a machine learning example may have even used this data before. It's a common example. I think in Python, you can import this data. It's like in a library in scikit-learn because it's such a common example. So can I classify the state of that tumor based on this data? That's really what I want to know. And this is a machine learning problem. You could say, You know, you could sit down there and write a hell of a lot of if statements, like okay, if the thickness is within this range and the size is under this value, but it's over this value, unless this value is over a certain value and then that one's under that one, then I think it's malignant. Otherwise, while and so on, I can go write that function, but one, who the hell wants to write that function? And two, who the hell has the expertise to write that function? Nobody. So what we're going to do is observe a hell of a lot of data and try to have the algorithm just do a bunch of statistics. Machine learning is just fancy statistics, by the way. Do a bunch of fancy statistics on all of that data to make conclusions about, well, based on all the data I've seen, if it looks like this, it's malignant. And if it looks like that, it's benign. That's what we want to do. So with genetic programming, we want to actually build that function. We want to have a function that might ultimately look like, okay, if this, then that, else this. It'll ultimately look like that a lot of times, but that's what we're going to do. We're going to use genetic programming to do that. So going back to what I was saying about how machine learning really is just an optimization problem, is I want to pick a function. I'm going to optimize the function that produces the best classification accuracy, for example. So it is just an optimization problem, which is depending on how we frame it. So the goal is to build a classifier to determine if this patient has breast cancer based on the observations. So what should the classification be? Like I was saying, if size is greater than 4 and the shape is 3 or 5, then malignant, else benign. If the thickness is greater than 4 and thickness is less than 9. If mitosis is 1, then malignant. I don't know. I can't figure this out. And neither can you. Not because you're stupid, but because who the hell can, right? So to do this, it would take careful study and a very deep understanding of the problem to build a classifier manually. Even then, how good is it going to be? But AI and machine learning are often used to automate the process of building these classifiers. The AI and machine learning would try to generalize the trends based on what it sees in the data, a lot of data. In order for these algorithms to work well, we need a lot of observations typically. And yeah, then we make the classifications based on all the observations. Most evolutionary computational algorithms are not designed to find models like this. They really are more, I'm looking for a solution to this problem. But like I was saying, depending on how we frame the problem, we can frame it as, I'm looking for a solution to a problem, and the problem is, what's a good classifier? So this is where genetic programming comes in. Okay, now, pause on that example. S expression. Okay, actually, before I jump into this, do we have any questions about anything? Yes?
How do you write a genetic program to take your operators, an if and stuff, and then have it work as in Python?
So, what we're going to do, so this is a very good question. So there's a lot of ways you can do this. In Python, it's actually relatively easy in Python compared to other programming languages, because in Python, you can serialize function without getting too far into the weeds. There's an operators library, and you can create if statements as objects and whatnot, okay, for lack of a better term. And you can even, not with pickle, for those of you reasonably familiar with Python, do you know what pickle is? No? All right, well, pickle is basically, do you know what serialization is? Really? Oh man, I think I need to teach that to people. In first year. Basically, you've got some data, some information, and you want to, your program's running and you've got, sorry, let me stand over here so you're not getting blasted. You've got some data, and you made it really obvious, I can't see. You've got some data, you got some information, and your program is running. But you know that whenever you close your program, you're going to lose it all. So you want to save it. Well, how do you want to save it? Well, okay, you can come up with some encoding. Maybe you could save the data as a CSV or something. But if you got a bunch of objects, let's say you've got some student objects that you want to save. How am I going to save that? Do I save it as Like, I guess I can save all the values, and really I shouldn't go very far, by the way, because my mic is over here right now. So don't let me walk around too much, because my mic has to charge. So you've got all these objects with all this data in it, and you want to, and it's, let's say you have a very stateful program, for better or worse, and you want to save it. So what do? Do you save it as plain text, and then you need to write a program that can parse, that can save the data to a file, and then you need to load the data back up and then parse it and save it as the object as you'd like, you know, that's how you would do it. Unless you use serialization, which is like, you would use a package called like Pickle to do this, but a lot of programming languages have this stuff built in. Basically what it means is you can save all that, like that object data to a file as the object data. So you don't need any fancy tool to encode the data and decode the data. It does that all for you. So it just simplifies it. So in Python, there's an extra library, so it's called Pickle, because you preserve the data, right? You pickle it, right? Which is fun. But there's like an extension to that one called dill, which I think is hilarious. And you can even like serialize functions and whatnot. So you can even save those things as functions that you can just call up and run, easy peasy. All that said, typically, genetic programming is, you know, you wrote a GA, right? Hopefully you didn't cheat, because you shouldn't have had to cheat to write a GA, because it's so goddamn easy. If you did need to cheat, you're in trouble. GA, they're easy to implement. Genetic programming systems, no. They're trouble. And there's a big reason there's a lot of issues, and there's a lot of reason this is relatively complex. So usually what we do is we use a genetic programming system. So you don't need to build the genetic programming algorithm from the ground up. You use an existing system that already exists that you just need to set a couple of settings for. I shouldn't say a couple, a lot of settings for, and then it already has all the heavy lifting implemented for you. So it makes it doable. So to answer your question, it's actually, my answer for how do you do it in Python, you just do it. You use Python to do that, because Python makes it relatively easy to do that, but in practice you're not going to do that. You're going to use the genetic programming system. The genetic programming system that we're going to use is called DEEP. Now, there are some problems with DEEP, but it is immensely popular. It was actually made from someone from the University of Laval, which is pretty cool. Somebody I went to school with knows the guy pretty well. I've never met him, but apparently he's a good guy. There were more than one person that were involved in making it, but one of the main guys. There are some problems with it. You could tell it was not designed by software engineers. They break a lot of Python conventions, which is pretty cringy. And I want to be very clear. It's wildly good. I use it all the time. Everyone uses it all the time. It's very good, but it does have some issues. But in general, it's fantastic, and there isn't a better one in Python, I think, right? In terms of how easy it is to get going. The documentation could be better. And it was all I'm pretty sure it was all really built around Python 2. And it works in Python 3 most of the time. And there's some stuff in the documentation that's just not true anymore. That's just still there. So you got to be mindful of it. All that said, everyone uses it. You can figure it out. For what we're doing, it's going to be perfectly fine. Hopefully that gives you a good sense of how am I going to implement it? You don't really. You use someone else's implementation. But you totally do it. Now, in other languages, it gets a little tricky. In other languages, you end up having to, depending on how you do it, you might have to have your, another friend of mine actually wrote a system that was pretty good. It was pretty, especially for its time. It was in C#. They wrote a system where all of their S expressions, the way it would get evaluated would be, they would have the code generate a class, and then that class could be compiled and ran, which is pretty interesting. But otherwise, you end up having it a lot of if statements to be like, okay, if your tree is this, you actually run this code, and then this, and then it's all these recursive calls. We're getting way ahead of ourselves, but fun question.
I tried to do that in C, like C plus, and I noticed that there's a lot of like, I went to deep eventually, but like, I noticed it was just like, if this, then that, and if this, and then it was like, I'm
Yeah.
just going.
Yeah, use deep. Yeah, but for this assignment.
Yeah.
Yeah. So you actually tried to be like, no, I'm gonna do it on my own.
Yeah, I thought, yeah, that was a good one.
Yeah. So look, if you got it working, fantastic. But yeah. Anyways, yes.
At what point in using something like deep do we have to like give citing and stuff? So we're not like figuring out.
All you have to do is say like, I use deep, and then I'll be like, yeah, I know, I told you to. I think. Did I say use it?
I think it says like in the class notes that that's what I'm using.
Okay, claiming that the base task.
Wait, it's not me, it's not. It is search bar. Oh, I didn't know it was.
For example, one of the tutorials for deep use. I didn't say use it here, but yeah, in the class notes I say definitely use deep. Do yourself a favor. Anyways, okay, as expressions. This is how we can encode functions programs as trees. All right, we've seen this. Here's a mathematical one. Here's one with some Boolean and math in it. Here's one with some form of like instructions. We can encode any function we want. Some of these are what we call like untyped, which is a nonsense name because it is typed. It's just single typed. This is only dealing with like numbers. This one we have mixed things, like we have numbers and Booleans, I guess, right? And this might even be some like arbitrary classification type, I don't know. And then here we've got like instructions, Booleans, and all this. It could get really complex. And as soon as you have like typed GP, which really is multi-type GP as opposed to one-type GP. Anyways, that's where things get really hairy, and that's where like, yeah, use deep. You don't have to deal with all that stuff. All right, so consider the above program function for the breast cancer identification problem. If whatever. So if true means it's malignant and false benign. So here's, right, if we go back up here and I take the first one here, this could be a classification, right? So how could I write this as a S expression? Well, I simplified it to actually not need the if. To just be a Boolean expression, all right? And here's the encoding. So I can actually encode that function as this tree trivially. That's it, right? If size is greater than 4 and the shape is 3 or shape is 5, it's true. It's malignant. Otherwise, well, then it would evaluate to false. Yeah.
How can you prevent like logical error when you do?
Can you be more? What do you mean?
Like if instead of shape it said size there. So if it was like
You
size-
can't.
Okay.
So stuff like that, what you would hope for is. So logical, like I know what you mean. Like if size is greater than 4 and size is less than or equal to 4, right? You're like, oh, what is that, right? So you can try to build some logic in to prevent that, but in practice, it's probably not going to be very beneficial. Because if it's a nonsense function, it's going to die off. It's going to have bad fitness. However, one thing we'll see, and I think we do talk about it, is this idea of bloat. And bloat is almost always a bad thing, but sometimes you end up with like imagine this was false and some giant tree. Who cares what's in that giant tree? It's false and anything is false. So it's useless. But sometimes by the nature of crossover, maybe there was like a really valuable subtree that ended up getting crossed over into this subtree, but it gets like not expressed. So you can get like non-expressed genes in the genotype, which is very interesting. And sometimes they might come back later in evolution. And like they'll talk about these things as like vestigial things, where it's like, at one point it may have been useful, because it's popping up in all these trees, but it's not expressed, so that's really interesting. That's getting into the weeds of genetic programming, but fun question nevertheless. All right, so in order to get started with genetic programming, we need to define, this is a new concept. We didn't have to deal with this with the GA. With the GA, we had a representation. Well, we're using trees here. We had genetic operators. Well, we need genetic operators that work with trees. We have evaluation. Okay, we need a way to evaluate these trees. But all of those core things are the same. But now, in order to make this work for genetic programming, we need to define a language. And a language is the set of operators and operands that are allowed to exist in the tree. So operators could be things like binary operators, plus, minus, multiplication, divide. Those are all like numerical ones. They take numbers and you give you back a number. Then we have comparison operators that might take things that are like numbers. They don't need to be numbers, but things with some orderedness to it. Less than, greater than, equals, equals, and Boolean operators, and an or. And we might have unary operators, operators that only take one value. So that could be something like sine, cos, e, not, right? Whatever we want, okay? And finally, we'll also have constants. And the constants, pardon me, not constants, we'll have the operands, which include constants and variables. So a constant could be like 4, true. And a variable can be like, well, the size of my current observation. Some value that, it has meaning, but the value can change depending on what we're looking at. So here's an example. Like 1.2 minus x. Well, this is a binary operator, this is a constant, and this is a variable, right? Just like any other function we've seen. Cool? So here's an example of a tree that has binary operators, unary operators, multiple variables, and some constants. Yeah? Yeah. So when working with mathematical expressions, our operators, they're going to be a lot of like arithmetic and numerical operators and operands. Cool? Cool. But then we have types and versus untyped. This should say typed. If someone wants to submit a PR, they can get famous. This should say typed. Notice that mathematical expressions work only with numerical values. All operators act on numbers. Well, as we already talked about, like with our breast cancer example, we're going to have to deal with like Booleans, right? Some operators will work, right? Like, we can use addition, but like why would, at the same time, if the sum of size and shape and mitosis is 4, then it's, well, does that even make sense? Why would we want to sum these things? Maybe it makes sense, I don't know. But sometimes, like maybe we need a lot more comparison operators there. As soon as we have comparison operators, we've introduced a new type. Because comparison operators can take numbers, but they give you back a Boolean. So you have typed genetic programming. We have to deal with all of this stuff. So for example, if shape is 4 plus 7, that is, like we know that this is an inadmissible statement. So our genetic programming system would need a way to avoid stuff like this from happening. Now, some asshole in here might be like, well, true is just 1. So this is admissible. No, come on. That's not what we mean here. That's an encoding issue. If shape is equal to 4, true or false, plus 7. What? That makes no sense. Okay? So we need to be careful. Whenever we're dealing with multiple types, our trees and our genetic operators, we got to be very careful not to make our trees inadmissible. There are two core ways to deal with this. One, you kind of ignore the problem and you just assign anything that produces a nonsense tree a really bad fitness value and they die off. Or you include some logic in your system to avoid this from happening in the first place. A lot of times in this class we've said, we can introduce logic, but it's not worth it because things will die off. But every once in a while, it's pretty damn worth it. You probably want to include the logic in the system to avoid inadmissible trees from arising in the first place because of the implications for the search space. Remember how we were talking about like with TSP? We could come up with any random permutation of the integers between 0 and n minus 1. And we could allow it to visit the same city several times. But we know that's an inadmissible solution. And we can include some logic in our system. That's not overly cumbersome. But we can include logic in the system to eliminate that from happening in the first place, thereby making the search space so much smaller. If you allow stuff like this, your search space, really what we want to have is a search space of all admissible functions to solve a problem, okay, which is going to be infinite. But if you also include all inadmissible solutions to a problem, well, that's a hell of a lot more. So you really want to make that search space as small as possible. Hopefully that's clear. Okay, your typical genetic programming setup is the same as a GA. You initialize the population, evaluation, selection, genetic operators, and termination. The key differences are really all built around the tree encoding. So here's like how the genetic operators might have to work for the trees. This is just like a single point crossover, right? But instead of picking a single point in like an array or a list, you pick a single tree node and you exchange the subtrees. Mutation, you select a subtree and you replace it with a new subtree. Cool. And you asked, AJ asked another time, like, well, could you just actually replace that with some other operator that's valid? Yeah, absolutely. You can do whatever the hell you want. And then finally, bloat. So do we have any questions? I'm kind of going quickly, but the key takeaway at this stage is it's just a GA, but we have to be clever with our encoding. Yeah?
Do you have to identify if it's numeric for like Boolean when you're doing your concept?
If it's typed, yeah. If it's typed, you gotta add all that logic there. Otherwise, you're gonna cross over and you make an inadmissible solution. I've seen genetic programming systems where what they do as a solution to this problem is they select two subtrees and they check, is it valid? No? Try again. Try again. Try again. Try again. Give up. That's fine. I've seen some where it picks something of a type and then maybe like it does some like heuristic search to find it. But as soon as, like, you gotta be careful how much logic you're adding because you wanna be careful about adding too much computational complexity considering that you're gonna let this run for how big of a population, for how many generations? Although that said, with genetic programming, it's tricky. Usually you have hilariously large populations for genetic programming, and it's weird. They say you're supposed to have really large populations for genetic programming, and you're really not going to run for a lot of generations compared to what you're used to with genetic algorithms. In my experience, and like such large selection strategies, or sorry, such large populations that they need to, like they invented new selection strategies to deal with the fact that these are huge populations. But in my experience, I've never needed to do that. I've actually always wondered why everyone says have large populations. Because for me, in practice, maybe I've just always gotten goddamn lucky. Now, I wrote my own genetic programming systems that were very specialized for things, so maybe it didn't turn into an issue because of what I was doing. But be aware that that's a thing. And what else was I going to say about that? Another thing, too, is mutation rate tends to be very low with genetic programming. Very, very, very low with genetic programming. So just FYI. That one I found to be true. Okay. Other questions? Yeah?
If you're working with something like a tabular data set, is the amount of leaves you can have on your tree restricted to like the number of attributes in
So say that again.
So if you're working with like a tabular data set, is the amount of leaves in the tree that you're working with restricted to the amount of attributes?
So it's not necessarily, but you have to be aware of, so ultimately, we have to consider, assume we only have binary operators. So unary operators, don't worry about it. We effectively have a binary tree. And we know binary trees can grow in size very rapidly in terms of the number of nodes in them, okay? You're doubling, it's exponential growth. You don't want your trees to be overly big. In fact, that's where we get on to bloat really quickly. You don't want your trees to be overly big because really big trees are very computationally expensive to evaluate. And if you've got a lot of generations in a big population, you're screwed. It's not going to happen. So people are very careful to limit the depth of their trees. And you want to limit two key factors. And there's actually things called decorators in deep that allow you to limit the depth of your trees and the number of nodes in your trees, which are obviously very related, but they are different because the trees don't need to be balanced. So you want to limit that. Like if I have a problem and the solution I'm looking for is like x squared plus 17 minus the sine of 5, right? If that's the solution I'm looking for, you know what, let's revisit this after I talk about bloat, because I think this will give some context to it. But to summarize the point I was going to make, you want to make your tree as small as possible, but it damn well better be able to be deep enough to find the actual like solution to the problem. Like when I was working on my PhD, I was looking for things. And I had a lot of like attributes, a lot of like columns. And for a while, like I was getting okay results, and then it hit me where I'm like, I allowed my tree to only ever get to a certain depth, which would mean it wasn't possible for it to express everything that it may have needed to. So I had to let my trees get even big, which was, it is what it is though. So we have to make sure it actually is as capable. Yeah. Okay, bloat. With genetic programming, so this is a very interesting phenomenon that people like will study. And we don't really actually like, it's not well studied enough where people have like concrete like theories on how it's just a lot of loose ideas, but there's this idea of bloat that you absolutely will see in practice. With genetic programming during evolution, the average number of nodes in the trees increases. It's always increasing. And it's usually, this comes with no meaningful increase in fitness. So your trees are getting bigger and bigger and bigger, but they're not getting better. So they're not getting better, they're getting bigger, and they take longer to evaluate, and that's just slow your whole search down. This is bad. So okay, this is problematic because the trees take up more space, they take longer to evaluate, they tend to overfit. That's a big one too. Bigger trees have an ability to overfit. Raise your hand if you know what overfit means. We talked about it a little bit, right? It's like when you're trying to classify the data you have so accurately. If I were to go outside and it just so happened that in the parking lot all the Nissans are blue, I might conclude if it's a Nissan, it's blue. Right? Because based on the data I have. But I just got bad luck. And that's a dumb observation. That's a dumb conclusion to make, that all Nissans are blue. So if I have a Nissan, it must be blue. Well, no, that's nonsense. But I might make that conclusion. That's like overfitting. Okay? Based on the data I have, I'm making conclusions that might not be true in general. Okay, yeah, the trees are difficult to interpret. That's a big one too. By the way, one of the huge benefits of genetic programming, this is big. So remember, genetic programming falls in the world, like evolutionary computation falls in the world of computational intelligence. In computational intelligence, these are the big guns for problem solving. And another one of the big guns for problem solving are your neural networks. And if you have a neural network that says this person needs neurosurgery right now, and the physician says why, and you go, because it's right 99.9% of the time, the physician goes, no, that's not good enough. But if you have something like a beautiful S expression for your thing, or something that looks like, for the breast cancer example, that where you can look at this and this has meaning to them in the context of what they're doing, they go, oh shit, okay, yeah, all right. If it's explainable AI, genetic programming is very explainable compared to other forms in the same class of machine learning AI. So this is a big thing with genetic programming, is the explainability-ness of it. Explainableness, whatever. Yeah. All right. So there are three explanations for why do these trees grow over time through evolution. Well, one, parents are selected for having a good fitness, right? Whatever fitness selection strategy we're going to have, you know, we have a propensity to select parents that have a higher fitness. Children with a function similar to their parents will also be relatively good, right? So if I have two good parents and they produce an offspring, if we like crossover, and that after crossover it's also good, okay? That's a good thing. It's possible that crossover might just make it garbage, whatever. But you have two good parents and they produce a good offspring, okay? It's possible to have two good parents that produce a bad offspring. But in the case where we have two good parents that produce a good offspring, when you have a very big tree, think about crossover, right? Like take a moment and think, I don't have an answer for you, but think to yourself. If I take think TSP, if I take two good parents and I do crossover, like how many times out of 100 do I get a similarly good child, a better child, or a worse child? Like what do you think happens more often? Probably, especially as evolution goes on, my gut tells me you probably get a worse child, right? Most of the time. Same with like mutation, but every once in a while you get a good one, and that's like the magic of the search. So it's good, and I'm not speaking just for evolutionary algorithms. I'm talking about evolution. It's good when a system is robust against negative changes. Okay? If a system exists, how do I word this? Because this is a big idea that I think you don't get until you get it. In order for me to exist, it needs to be robust against dying. Okay? I have children. In order for those children to exist and persist, they also need to be robust against dying. So, the process of producing offspring, the process of having crossover, has to make it such that, the offspring are also good, because if they died off, well, where are we going to get, right? So systems, there must be something built into the system. I'm trying to think of how to work, because this is a big idea. But maybe, hopefully you get what I'm saying. If two parents had crossover and they produced a kid that wasn't good, then who cares? It dies off, right? If these two trees are selected with hyphaeus and they produce a child that's good, it persists. So what is good? Well, something that's robust against change. And what's robust against, something that's robust against getting bad is something that's robust against change. And something that's robust against change is big-ass trees. Because if I have a big tree, and I do crossover, in big trees there's a lot of parts that might be unexpressed. The change might be effectively, think of a big tree, and if you have a small tree, and you change, a binary tree with two nodes, and you did crossover, you've changed half the goddamn tree. If you have a big-ass tree and you change some subtree, that's a tiny change. So they necessarily get bigger. Bigger trees are better because they're going to be robust against negative change. And almost always change is bad. Is this clear? If it wasn't true, these are some of the big ideas in evolutionary computation that you kind of have to spend time thinking about. A big tree is good not because it's good. It's good because it's robust against getting bad. That's kind of it. And if it doesn't make sense, spend the time thinking about this, because these are big ideas. Removal bias theory. Unless subtrees, useless subtrees with no meaningful function may exist within the tree, right? Like this. Some subtree or true. It doesn't matter what's over here. It doesn't. Anything or true is always true. So with larger trees, there's a higher chance of having these useless subtrees. And applying genetic operators to these useless subtrees has no impact on the fitness chromosome. So this, going with replication accuracy theory, they kind of go hand in hand. And that's just okay. And then the nature of program space theories. This is another interesting thing too. With a fixed language, there are more larger programs. The number of larger programs with a given function is greater than the number of short programs with the same function. For example, what is this program? This program is 4. Okay? How many different ways can I represent the number 4 if you have this as an example? Well, you can have the number 4. You can have 1 plus 1 plus 2. You can have 1 plus 1 plus 1 plus 1 plus 2 minus 2. You can have, and so on and so on and so on. There just is more big trees that mean the same thing as smaller trees. So that's another thing too. You put these things together, there's this natural tendency towards these unnecessarily large trees for your genetic programming system. Yeah, okay, cool. Like everything, there's no right answer, but the popular strategies are managing bloat. How do you manage bloat? Well, you can set limits. Set tree depth limits, set tree node limits, use specific genetic operator rules to prevent them getting too big, and add tree size as part of the fitness measure. This is a big thing too, actually. What people will do is they'll turn their problems into multi-objective problems, where they want your functions to be good while also minimizing the size of the tree, which is interesting. You have this like selection pressure. If you have 2 equally good functions, but one smaller than the other, pick the smaller one. Okay, for next class, if you don't come prepared, I might ask you to leave. Read up on deep and get it going. Get it ready to go. Because next class, we're just going to play around with deep. And if you show up and you're like, I haven't gotten it working, I'm going to ask you to leave. And you can come back when you got it ready. Cool? Cool. Cool. All right. See you later.